Hi there. In this video we're going to go through the magnetic fields topic, and we'll start off by talking about how they are created. So to create a magnetic field we need a moving charge that will produce a magnetic field, and of course current in a wire or in a conductor, current is just made of moving charges, so if we have a current carrying conductor that will also produce a magnetic field. So you need to know that those kind of things will produce a magnetic field, and also the shape of the magnetic field around various things. So here we go. A straight current carrying conductor like this one here has a magnetic field around it in the shape of circles like this. We use the right hand rule to confirm the direction, whether it's clockwise or anti-clockwise. So you should be able to confirm by putting your thumb in the direction of the current and then your fingers curl in the direction of the magnetic field. You should be able to confirm the direction of the magnetic field there. Far more commonly in a test or exam situation, you'll be asked to draw the magnetic field around a current carrying conductor that is represented as a circle with a dot across. Dot represents current coming out of the page. So when you're doing that, you put your thumb towards yourself because your thumb is the direction of the current. It's going outwards. You should be able to confirm that the magnetic field will go anti-clockwise like that. And if the current were going into the page, you'll be pointing your thumb away from you, and you should be able to confirm that the magnetic field is going clockwise in that direction. Some things to remember is that the magnitude of the field is represented by the number of lines per unit area. So there's more lines per unit area the closer we are to the conductor, so the field is stronger. And the direction of the arrow shows the direction that the north pole of a magnet will be forced if we're placed at that point. So if that green dot was the north pole of a magnet, it will be forced to the right. And that is the direction of the force on it at that point, because that's the direction of the magnetic field at that point, at a tangent to the line. If you were to draw these magnetic field lines, it's 3 concentric circles. So you can start off by doing one that's on the inside, try and make it nice and close to the conductor. Then you do the one that's furthest out, just so you can define the space that you're working with. And you just want to draw the in-between one that's slightly closer to the innermost one, and that shows that the distance increases the further out you go, so that the magnetic field strength is decreasing the further out you go. If we have lots of loops of wire, we can make a solenoid where the current is going to zip round and round and round, and then the magnetic field around a solenoid looks like this one here, which is similar to what a magnetic field looks like around a bar magnet, where we have a north end and a south end, because that's really what a solenoid is for. We can run a current through it and create an electromagnet. We want to determine what direction the arrows are going to go. To do that, we need to know which end is the north end, which end is the south end. The magnetic field goes away from the north end, comes back around, and into the south end. To do that, the easiest way to do it is to grip the solenoid such that your fingers are going in the direction of the current. So in this case here, you will grip it kind of like this. So your hand's making a weird shape because you want your fingers to go into the page, and then you should find that your thumb is at this end of the solenoid where the north end is. So we get the arrows coming out of here and the arrows going into the south end like that. Important to note for when we're drawing the magnetic field is that inside the solenoid the magnetic field is pretty much uniform, so we do the magnetic field lines the same distance apart and they're all parallel. I like to start off my diagrams by doing 4 lines and then doing the loops to join each end of the line to the other end to do my magnetic field outside the solenoid. Try and ensure that the distance from here to the solenoid is increasing as you go to the next field line, to show that the magnetic field decreases in strength the further away you get from the solenoid. That's how we do the magnetic field around a solenoid. As we move on, we can talk about the magnetic field around a single loop of wire, which this diagram shows it rather well, where and the current is going around the loop, and we got the magnetic field like this. Just do a note and compare that to the field for a solenoid, like this one here. It kind of looks the same, it's just that the interior bit isn't as long, and it's stronger towards the center. So if we're doing the magnetic field around a single loop, it's kind of similar like that for a solenoid, but kind of mixed between that and that for a single wires. So to do that, you can try and use your right hand rule to determine the direction of the magnetic field for the top wire and the bottom wire. And if you do that for this one, you should be able to determine, like this top wire, you'd point your thumb away from yourself and you should determine the magnetic field will be going clockwise, and for the bottom one it's going anti-clockwise, such that inside the loop all the field lines are going in one direction, and outside the solenoid they're curving back and going in the other direction. So we can represent it like this. We can also represent it in this diagram down here, where you can actually see the loop and not just like imagine it splicing through the page. So in this case here, what's nice to do is to again put your thumb in the direction of the current, and if you point your thumb up the top here, you should find that your fingers are curling such that above the wire the magnetic field is traveling towards yourself, and inside it's traveling away from yourself, I think. Let me just check that. Yep, okay. So inside I need to do some dots, and I might do several dots in the center just to show that's where it's the strongest, and they get further apart and less strong as we get closer to the wire. And then outside I'm doing some crosses to represent that the direction of the magnetic field there is into the page and getting less strong as I go out further. This one here is a bit frustrating to do, but just try and do more crosses or dots in the center of the wire like that. And this in my mind is a bit easier to do, but we need to be able to work with both of them for a single loop of wire. Turning back to our straight conductor, there is a way we can determine the strength of the magnetic field at a specific point away from a straight current carrying wire. So there's an equation for that, which I'll introduce to you, and we'll talk about how that works. So to get our head around what we're about to do, if we have a single wire like this one, I can look at specific points around this conductor. Like I might look at, just choosing my color. I'll go green. There we go. I might look at this point here. Let's call this point A. This point here, we'll call that point B. And maybe, just to be a bit complicated, that point over there, we'll call that point C. So you must recognize that if I was to draw vectors to represent the direction of the magnetic field strength at those points, at this point here for A, the magnetic field at A is going downwards at that point because that's at a tangent to the line at that point. If I look at specifically point B, the direction of the magnetic field at point B will be going to the left, like that. So that will be the magnetic field strength at point B there, BB. And for point C, a tangent to the line at that point would be going up that way, and that would be the magnetic field strength at point C. So whatever point we're talking about, the magnetic field is going in a specific direction, not just like clockwise or anti-clockwise. So it's important to recognize that if we're focusing on specific points. So we can determine the magnetic field, the direction of it around a wire, by visualizing these circles and thinking about, well, at whatever point we're looking at, what direction is the magnetic field going at that point, and it's going to be a tangent to the line in the direction of the arrow. As for the magnitude of the magnetic field at these points, we can represent that using a quantity, a number. So to do that, we use our formula for calculating magnetic field strength, and that is this one here. U naught over 2 pi, and that's being multiplied by the strength of the current over the radial distance there. So, for example, if I wanted to calculate the magnetic field at point A, I would need to use the current, whatever the current is through this wire, and I would use the radial distance just for point A. So I'd actually have to use this distance here. So I'll do it in green. So I would need to use whatever this distance is here. That will be the radial distance specifically for A. So I'd have to use RA in that equation there, and that will give me the magnetic field strength at point A. So we need to use the distance for A. The current is whatever current is flowing through that wire, and that will tell me the magnetic field strength in Teslas. We'll measure our magnetic field in Teslas. For the direction of that field, this equation won't tell us that. We have to think about the situation, and then we have to realize that at this point here, it has to be going down. That's the direction of the magnetic field at that point. Moving along from that discussion, we can talk about what if we have two current carrying wires. If we call this IA, if it's wire A, and if we call this IB for wire B, and I want to determine what the total magnetic field strength is at this point here. Let me just talk about the direction of the magnetic fields at this point first. We're going to ignore wire B for a second and pretend it doesn't exist, and just think about the direction of the field around this current carrying wire A. And if you use the right hand curl rule, you should be able to determine that it's going clockwise around A. So if I look at the way I'm moving my mouse, that means at this point the direction of the magnetic field is to the left. So I'm just going to draw an arrow here and make it go to the left, and that is the magnetic field that's coming from wire A. For wire B, I'm just going to forget wire A for a second and just focus on B. Again, using the right hand curl rule, I know that the magnetic field is going in this direction, which means at this point the magnetic field is going to be going to the right, because it's going anti-clockwise for wire B. And my mistake, I'm not going to do that vector for as long, because it's further away from wire B, so the magnetic field strength at that point isn't going to be as big. So BB might be only about that big. So that's our direction for those two. We can determine the magnitude by using the same formula I was discussing before. To calculate what this magnetic field strength is, we would use this equation here. With that as the constant value, IA, we'd use whatever the current is going through A. We'd use the distance from A, so this distance here, to calculate the magnetic field strength due to B. Again, I'll use the same equation, but I'm using current for B, and I'm using the distance from B, and that will give me the magnetic field strength at this rate, this one here. So now I've got two magnetic fields at that specific point. If I want to determine the total field strength, I would need to add or subtract those values from each other. In this case, they're going in opposite directions, so one's going to subtract from the other to get us our overall total field strength. Just as an example, if it was calculated that BA was, well, I don't know, 1.7 Teslas, and for B, because it's further away, it shouldn't be as strong, so maybe that's like, I don't know, 0.4 Teslas. Now for our direction, remember that is going to the left, this is going to the right. If we look at our vectors in our diagram there, and that means that overall the magnetic field strength at that point should be going to the left, but not this much, it's going to be less 0.4. So to calculate the total, we're adding as vectors A and B, but because one of those arrows is in the opposite direction, we end up subtracting one from the other. So we end up doing 0.7 take 0.4, which would be, what, 1.3 Teslas going to the left, like that. Very good. So that concludes this video on magnetic fields. Thank you very much for listening, and I'll see you next time.